The Boeing 787-10 looks like just a stretched Dreamliner. Longer fuselage, more seats, same technology. So everyone assumes it is the simple version, but they are completely wrong. Here is why the Boeing 787-10 is more advanced than you think. Understanding the Boeing 787-10 requires understanding what makes the entire Dreamliner family revolutionary. These aircraft changed commercial aviation fundamentally. The Boeing 787 was Boeing's $30 billion bet on the future, an all-in gamble on radical new technology, and it paid off spectacularly. The material composition tells the story immediately. By weight, 55% of the Boeing 787-10 is made from composite materials like carbon fiber reinforced plastics. This makes it the first commercial airliner made primarily with these new age materials. Only the Airbus A350 rivals this composite usage. Why are composite materials so desirable? Carbon fiber provides incredible strength, up to 5 times stronger than steel at 1/5 the weight. But these tiny fibers cannot create solid parts by themselves. They must be bound together with plastic resin to form solid material. Otherwise, they just form strong but flexible fabric. That flexibility as fabric is exactly what makes composites so useful when creating the precise, elegant curves of aircraft. With the right tooling and design, composite components can be made into almost any shape imaginable. The Boeing 787-10's fuselage is created by wrapping carbon fiber tape impregnated with plastic resin around a rotating mold. This automated tape laying process precisely controls the overlaps and fiber orientation. This ensures maximum carbon tensile strength to resist internal pressure loads and longitudinal bending loads the fuselage experiences. One problem with this manufacturing method is that the part needs placement inside an oven to cure the resin. This hardens the plastic and creates solid composite structure. Ovens the size of a wide-body jet airliner fuselage are not exactly common. This requires massive upfront investment to build customized ovens large enough to fit the part, but the benefits are well worth it. The first and most obvious is the strength carbon fiber provides. Previous generation airliners are typically pressurized to an equivalent of 8,000 feet, high enough that lower pressure reduces oxygen intake. Your stomach bloats as internal air pressure exceeds external pressure. This is uncomfortable and exacerbates jet lag effects. But thanks to the Boeing 787-10's stronger fuselage, it can increase internal air pressure to an equivalent of 6,000 feet, 25% lower in altitude, about 7.3% higher in pressure. This makes the journey dramatically more comfortable. The Boeing 787-10 also features absolutely massive windows, much larger than equivalent aluminum airliners. An aircraft made primarily from aluminum, having holes this large in metal panels would result in stress buildup at window boundaries. Over repeated pressure cycles, tiny imperfections in metal can grow into larger cracks and eventually fail. Holes this large in aluminum airliners would severely shorten the plane's flying career. But it is not a problem for the Boeing 787-10, thanks to composite's relative immunity to fatigue. The carbon fiber construction provides plenty of benefits for airline operators too. Because the fuselage is just one massive part, Boeing eliminated all joints and fasteners needed to join them together. Sections that used to be made up of 1,500 aluminum sheets riveted together using 40 to 50,000 fasteners are now just one massive carbon fiber section. Carbon fiber's strength to weight ratio already makes the fuselage lighter, but eliminating joints and fasteners makes it even lighter. The reduced weight reduces fuel burn significantly. This fuselage is also incredibly aerodynamic because it does not have thousands of little bumps and ridges from joints and rivets. These surface imperfections make the plane's surface rough and cause more air disturbance, increasing parasitic drag. The Boeing 787-10's wings showcase composite advantages beautifully. The main structural member of a wing is the wing spar. Its primary role is resisting upward bending force during flight. It is essentially just an I-beam, a shape optimized to resist bending loads. The wing spars of the Boeing 787-10 are constructed from carbon fiber composites. The ribs, the structural members connecting the two spars that support the wing skin, are machined out of solid aluminum plates. Carbon fiber composites have an important quality that makes them perfect for aircraft wings: their maximum elastic strain. There are two types of deformation: elastic and plastic deformation. Elastic means the material snaps back into original shape after load removal, like an elastic band. Plastic means it permanently deforms and will not return to original shape. Carbon fiber composites can deform further before they reach plastic deformation zone at about 1.9%. Aircraft aluminum begins permanently deforming at less than 1%. This means we can bend carbon composites nearly twice as much before causing permanent damage. This allows Boeing to create thinner, more elegant, and more efficient wings for the Boeing 787-10. But here is where the Boeing 787-10 faces unique challenges. It is the longest variant of the Dreamliner family. This creates specific engineering problems. The Boeing 787-10 stretches 224 feet in length. That is 18 feet longer than the Boeing 787-9. This additional length enables the aircraft to carry significantly more passengers. The Boeing 787-10 can accommodate up to 330 passengers in typical configurations. This makes it ideal for high-density routes, where capacity matters more than maximum range. But making an aircraft longer is not as simple as just adding fuselage sections. The longer the fuselage, the more it wants to bend and flex during flight. This is basic physics. Think of it like a diving board. A short diving board is stiff, a long diving board flexes dramatically. The Boeing 787-10's extended fuselage creates similar challenges. Boeing had to ensure the Boeing 787-10's structure could handle these additional bending loads without adding excessive weight. This required careful analysis and reinforcement of specific structural areas. The wing attachment points experience higher loads on the Boeing 787-10. The longer fuselage creates more leverage acting on the wing-to-body joint. Boeing reinforced these critical connection points. The tail section also required attention. The Boeing 787-10's longer body means the tail sits farther from the center of gravity. This increases control surface effectiveness, but also structural loads. Ground operations present unique challenges for the Boeing 787-10. The longer fuselage means the tail sits lower to the ground during takeoff rotation. If pilots rotate too aggressively during takeoff, the tail could strike the runway. This is called tail strike, and it can cause serious damage. Boeing had to carefully calculate the maximum safe rotation angles for the Boeing 787-10. Pilots receive specific training on proper rotation techniques to avoid tail strikes. The landing gear positioning also required optimization. The Boeing 787-10 uses the same four-wheel main landing gear configuration as other Boeing 787 variants, but the longer fuselage changes weight distribution slightly. Boeing positioned the landing gear precisely to ensure proper weight distribution and prevent excessive loads on any individual gear assembly. Despite being the longest variant, the Boeing 787-10 actually has the shortest range of the Dreamliner family. It can fly approximately 6,430 nautical miles. This is significantly less than the Boeing 787-9's range of about 7,635 nautical miles. Why the reduction? The answer is fuel capacity and weight. The Boeing 787-10's longer fuselage creates more internal volume for passengers and cargo, but it does not significantly increase fuel tank capacity. Additionally, the longer, heavier airframe burns slightly more fuel per mile. The combination of similar fuel capacity with higher fuel consumption reduces maximum range. But this trade-off is intentional. Airlines use the Boeing 787-10 on high-demand routes, where capacity matters more than extreme range. Routes like transatlantic or transpacific flights between major cities. The Boeing 787-10 excels in these missions. It carries more passengers than the Boeing 787-9 while maintaining the fuel efficiency and passenger comfort advantages of the Dreamliner family. The cabin altitude and humidity advantages apply equally to the Boeing 787-10. Passengers experience the same 6,000-foot equivalent cabin altitude, the same improved humidity levels, the same reduced jet lag. But they get these benefits while airlines carry more passengers per flight. This is the Boeing 787-10's value proposition: maximum passenger capacity with Dreamliner technology. The Boeing 787-10 also benefits from all the advanced systems developed for the Dreamliner family: the no-bleed air architecture, the electric cabin pressurization, the advanced engine technology. These systems work identically on the Boeing 787-10 as on the smaller variants, but they must handle the demands of a larger, heavier aircraft carrying more passengers. The electrical generation capacity remains the same, 6 generators producing 1.45 megawatts of power. But this power now supports a longer cabin with more passengers requiring environmental control. Boeing's engineers ensured the systems could handle the increased demands without compromising performance or reliability. Manufacturing the Boeing 787-10 also presented challenges. The longer fuselage sections are more difficult to transport and assemble. Boeing's global supply chain had to adapt. The Boeing 787-10 is assembled exclusively at Boeing's South Carolina facility. The longer sections cannot be transported easily using the Dreamliner cargo aircraft that move Boeing 787 components globally. This manufacturing concentration in South Carolina required Boeing to build additional capacity and expertise at that location. The result is an aircraft that looks simple but required solving complex engineering challenges. The Boeing 787-10 is not just a stretched Boeing 787-9. It is an aircraft pushed to the limits of what the Dreamliner platform can achieve. Longer fuselage, higher passenger capacity, complex structural loads, challenging ground operations. Boeing solved all these problems while maintaining the revolutionary characteristics that make the Boeing 787 family special. Composite construction, advanced systems, passenger comfort, fuel efficiency. The Boeing 787-10 represents Boeing's engineers asking how far we can push this design, and then engineering solutions to make it work. Airlines love the Boeing 787-10 because it combines capacity with efficiency. They can carry more passengers while maintaining lower operating costs than previous generation aircraft. Routes that previously required larger wide-bodies can now be served profitably with the Boeing 787-10. This opens new possibilities for airline network planning. The Boeing 787-10 is more advanced than most people realize, not because it has different technology than other Boeing 787 variants, but because it applies that technology to a more challenging design. Longer fuselage, higher capacity, complex loads, difficult ground handling. Boeing engineered solutions to all of it. The Boeing 787-10 represents the Dreamliner platform pushed to its absolute limits, and it works beautifully.